Today we have the pleasure of hosting Dan Grollman with us. Dan's from Plus One Robotics, and he's going to be talking about a human-in-the-loop approach to parcel variability. So Dr. Grollman leads the core team for Plus One Robotics, and he has over a decade of experience in productizing human-robot interaction, and his work centers on applying academic research to commercial problems. And at Plus One Robotics, he focuses on building systems that enable robots and humans to continuously learn from each other. So thank you very much for joining us today and agreeing to present, Dan. I'm stop sharing and let you start your presentation.
Wonderful. Okay. So yes, I'm Dan Grollman. I run the core team at Plus One Robotics. I'm talking about human-in-the-loops management for parcel variability. I'll start by saying feel free to jump in and interrupt with questions anytime. I am thrilled to be here. I've attended a few of the talks in the past, and I always enjoy when they are engaging and interactive. So let's start with what is parcel handling, since I assume many of you don't spend your time hanging around in logistics warehouses the way I do. So we do two main things. We do depalletization, which you see here on the top, and induction, which you see here on the bottom. And the task is to use an arm to pick up an item, one item at a time, and transfer it from one place to another. You may have heard this as pick and place. That's what we're doing for parcels. We use suction grippers to actually grasp the items. We use off-the-shelf arms made by Fanuc, KUKA, ABB, any one of those arm manufacturers to move it. We use off-the-shelf RGBD cameras, if you're familiar with the Intel RealSense or the Azure Connect. There's a few others in a similar vein. And then we use artificial intelligence, machine learning, and standard computer vision techniques to find the thing we need to pick up. And what we do, and why this is human in the loop, is we use humans to handle exceptions. So just again, if you want to think about it in your head while I'm talking, we get a camera view of this palette of objects. I don't know if people can see my mouse if I wave it around. Yep, so we get a palette of objects. You've got your suction cup. You got to figure out where to put your suction cup to grab the thing. And then you put it one at a time on a conveyor belt. Induction is the same task, but your objects are sort of less well organized. They come down a chute. They're a huge pile. Find one thing, pick it up, put it on the outbound. That's the task. And the argument we make is that parcel handling, good automated parcel handling, is all about handling your variation, right? So automation in general in industry and manufacturing started with, let's just do this one thing exactly, repeatedly. If you think of arms welding cars in warehouses, like in this picture, they're doing the same path. They're moving the weld along the same path every single time. And machines, I'm not even going to call them robots yet, but the machines are really great at this. You say, this is the path you follow, it doesn't. Well, then things got a little more flexible. So we started looking at the same object, but in different scenarios. So we know we have a pile of gizmos or widgets. We want to find one of them. And the way you did this is you had a good model of your object. You had a CAD model, and you could use computer vision to find out where that was. This is sort of where parcel handling started. We're going to say, well, what if this object is a box? We can put whatever we want in the box, and then we can handle parcels. We got a bit more complicated. We said boxes can be different sizes, but still it's a box, right? They all sort of look the same. And then, of course, we got more complicated from there. And now we handle different types of containers. This is an actual induction input. You see we have envelopes, we have padded mailers, we have boxes, we have envelopes that say FedEx on them, we have envelopes that are yellow, basically anything that might show up in your mailbox or on your doorstop. That's what we have to handle. And this now gets even bigger. And I'm waiting for someone to ask me to handle one of these things. I don't know if you all remember them from when you were kids. They're little wiggly toys that sort of just fall out of your hands. And this is sort of what's coming, because there's this new thing called ship an original container, which is you just ship as the thing is without repackaging it. And so variation is just increasing every day. So If you were a warehouse logistics manager and you came to me and asked, can you automate my system? Can you put in an arm and a camera and pick up things and put them down? My first question to you is, what's your distribution? What is the distribution of things that we need to be able to handle? Is it the same object every single time? Is it a set of objects or something else? And the response we tend to get is, we don't know. We don't track that, or it's changing. And this is entirely true because the things you have to handle change all the time. There's seasonal changes. So people order different things, or people send different things through the logistics system in winter versus summer, right? Also, people have discovered that advertising on packages is a great business, but that of course changes what they look like. And we make new things all the time. So new stock keeping units, that's what SKU stands for, show up, and now you have to handle those. So I have a little picture to help think about this. This is a distribution of packages, just a distributional space in 2D for color and size, right? Two easy dimensions. Today, maybe this is what you handle. You handle boxes, and the brown has some variance and the size has some variance, but this is the distribution of objects you need to handle, the distribution of parcels. But along comes Black Friday. And all of a sudden, people are buying lots of televisions because they all went on sale at Costco, right? Well, now you have to handle larger boxes. Your distribution has shifted. And then along comes a new movie, and someone thinks it would be fun to advertise on your box. And so now you have a box that's a completely different color. It's the size you've seen before, but it's all colored differently. How does your system deal with the fact that your distribution has changed? That's the question we have to deal with. And so the key takeaway here is that the distribution of things is not constant. It's going to change over time. And so the question isn't what's your distribution, but it should be how does your distribution change? The other thing you have to worry about is these, so-called 1 in a million events. You may be familiar with the Pareto principle or the 20-80 rule, which states that 20% of your scenarios account for 80% of the requests. So if you think of scenarios as, box sizes, almost all of your boxes, 80% of your boxes look the same. But there's that 20%, or there's that 80% of boxes that account for 20% of your scenarios that are different. And you can't have one solution to fit them all. Because honestly, when you're doing parcel handling for logistics, you can send anything. And given a long enough time frame, many unusual things will happen. So here's one of my favorites from a different domain. This is an autonomous vehicle driving down a road, and you hopefully be able to see it. But in front of this car, there is a duck being chased by a woman in a wheelchair or a motorized scooter. This is not a scenario that I would have anticipated having to deal with if I was designing this autonomous vehicle. And this is not a scenario that appears in training data. We'll get to that in a minute. This is an unexpected thing. But when you're out in the real world, operating for long periods of time, you need to expect the unexpected. And if people still remember DuckTales, that's what they taught us. What does this mean in terms of distribution? Well, this means your distribution is long-tailed. Here's what that looks like. Most of the things we see are brown boxes, envelopes, and bags. On the vertical axis is just count. That is, again, 80% of everything we need to handle. But there's all these edge cases, all these things that we see maybe 1 or 2 or 3 or maybe a dozen of. Boxes that are shaped like hexagons instead of cubes. Brightly colored boxes. Boxes that have dog patterns on them because it's dog food. Or someone actually trying to send a potato through the system. Right? So the long tail means that we have to deal with these things very rarely, but we still need to deal with them. So this leads to a conversation about how does your system need to be structured. Do you want a universal system or an adaptable system? Now, I frame this as the difference between being able to handle anything versus being able to handle anything. So for a universal system, you spend a lot of time up front considering all of these edge cases. How are we going to handle this? How are we going to handle it when a duck runs across the road? How are we going to handle it when a new advertisement comes out and changes the color of our boxes? Or how are we going to handle it when someone ships a potato? A universal system can do a lot of things, but many of those things will either never need to be done or only need to be done once or twice. But the impetus behind using a universal system is you can build once and use it forever. Once you have a universal system, you never need to touch it. You measure the success of a universal system by how much of the space can we handle. So here's an image of a universal, near universal system. This is that same size versus color distribution we saw before. And I'm saying here in blue, this system can handle most things, just not around the corners. Contrast that with an adaptable system. An adaptable system focuses only on what actually occurs. You don't have to spend any time worrying about what might happen. You focus on what actually happens. And the goal, of an adaptable system is to quickly absorb new things that you see into this realm of competency, this blue circle, this blue shape here. Unlike a universal model or universal system, an adaptable system needs to be built iteratively. You need to react to things as they change. And you measure adaptability by how quickly can you absorb new things. So you might start off with a system that looks like this. It only handles that initial brown box case. But an adaptable system can very quickly change its realm of competency to handle new things. So why would you want one versus the other? Before I get into that, let me tell you about symbiotic human AI system. Right? I've mentioned system, I've mentioned model. Sometimes those are interchangeable. The idea is that in a symbiotic human AI system, humans and autonomy work together. Right? And this is what we see in practice. In practice, no autonomous system works alone. There's always a human somewhere. So the understanding is that the AI vision or the mechanical system is not 100%. It can't handle absolutely everything. It is not purely universal. So humans have to deal with exceptions. And the way humans do that is they can physically go out and deal with the thing. They can sort the input before it gets to the system. There's a few different ways humans can get involved. The idea is that the system, the human plus the autonomy, can handle anything, even though the autonomy cannot. So the real question is, how universal does the autonomy need to be? And this is driven by the speed, frequency, and cost of human interventions, and also some learning. So let's talk about human interventions. I view it as a seesaw. If human interventions are very expensive, you don't want many of them, right? Because it just costs money. And this is also time. Like if humans need to physically be there, if they need to travel, if they need to sit with the system a long time, that costs money, and that costs human effort. So you try to minimize that as much as possible. This means you want universal autonomy, or you want near universal autonomy, because you cannot afford to have humans be involved. Conversely, if humans are cheap, if human interventions can be done quickly and easily and cheaply, you can have an adaptable autonomy, because now you can afford to have humans step in more often and teach the system or deal with its shortcomings. How do you get inexpensive human assistance? Well, the way we do this in our system called Yonder, which I'll show you in a minute, is first thing we do is we make the human be remote. Right? So the human no longer needs to physically interact with the system. So this removes any sort of transit time of the human moving their physical body to be near the system. It also practically allows us to shift labor geographically. So if something is, happening at 10 p.m. in one place, it could be in the middle of someone else's workday somewhere else. So you get to follow the sun, and that has cost benefits. We also reframe what we think the human, how we think of the human, not as a problem solver, but as an oracle. They're going to solve the same issue that the autonomous system is trying to handle. And this way we can leverage some learning. So let me show you some examples here. This is an example of a picture we might get from a depalletization cell. You can see a bunch of boxes sitting on a pallet. The boxes are shiny from tape. There's black boxes, there's brown boxes. It's a complicated scene. This is sort of what we really want to get. This is a vision system telling us that these are the boxes. They're all colored. They're all segmented separately. This is a really nice output. We don't actually need all this information. The way our system works is you're picking one box at a time. So we just need one. So the question we have is this image over here on the left. And the response that we sort of want is this image on the right, which is here is a box that you can pick. We put this all together in a system called Yonder, which is remote human real-time interventions for autonomous vision exception handling. It's a mouthful, so we just call it Yonder. Heaps of items come into our arm. If the arm knows how to handle it, if the system can handle autonomously, it just does and individuates and singulates the objects. If something new happens, if this is a long tail event, if the distribution has shifted, if the system, the autonomous system just doesn't know what to do, we ask these wonderful humans over here who sit at their computer, click some buttons, and provide the same response the autonomous system would have done. What does this mean? Well, I mentioned, people usually go out to deal with this issues with the cell, with the system. And I said we make that remote. Well, we can't make everything remote, right? So we divide exceptions into two sort of scenarios: vision exceptions and mechanical exceptions. Traditionally, these are all handled by walkouts. And a walkout is a human physically walking into the system, dealing with the issue, moving the object, picking the thing that's difficult, fixing the gripper. What we've done is we've split this. And we've said any vision exception now we can handle remotely. So we can do those without walkout. The mechanical stuff, you still need to physically interact. Those still require walkouts. This opens up some stuff. With remote human intervention, this now allows us to pursue adaptable models. So when interventions were expensive, remember that seesaw, you want to minimize interventions as much as possible because they just cost too much. And you want this universal model to handle as much as possible. And you have to spend a lot of time upfront conceptualizing and training all these rare cases. Now that we have cheap human interventions, we can tolerate more exceptions. Well, that means our model can be less universal. We can even start with no model at all. We then collect less data, but the data is focused on where the model performs poorly. Well, that means we have lower annotation burdens. Lower annotations and less data means faster training. This is all in the context of ML. Leads to quicker model updates. And now we can achieve an adaptable model. What's this look like? This is sort of the cycle that we're proposing. We start with a non-universal model, or even no model at all. We collect just the data where the system doesn't perform well. These are the things that are passed to the human when the autonomy doesn't know what to do. We only annotate those minimally. That's that single, we're just going to tell you this one thing that you need. Well, that leads us to quicker training. That leads us to a new model, which we can then deploy, collect more exception data, and we have this adaptation loop. This may strike some of you as very similar to the ML data cycle, which is basically the same thing: collect, annotate, train, deploy, right? There's a study came out in 2020, so 3 years ago now, that the majority of ML time in production is spent here in collecting and annotating your data. 80% of your time cleansing, labeling, augmentation, aggregation, identification. And so people have focused a lot of work on how do we make this portion of the system go faster. Well, you used to have to collect all your data in situ, right? You used to have to go on site and collect data for training from doing the thing you actually cared about. And very clever people came along and said, well, we could just build a lab and collect more data. So for us, that is, we could go on site to a depalletization or induction cell and collect that data, or we can build our own, and then we can feed it whatever data we want. If we're concerned about black boxes, we can just make more black boxes and collect that data. And then some clever people came along and said, actually, we can just simulate all this. So if you're familiar with sim to real training, you actually just build a simulator of the scenario you care about. That could be self-driving, that could be induction, that could be depal, and you use that to generate the training data. How do you get your annotations? Well, the gold standard is still humans. Humans sit and look at these images or look at this data and provide the annotations of the things you care about. Nice thing about simulation is it gives you this for free, right? Once you have your simulator set up, it gives you the annotations. Interesting thing about simulation is you have to be really careful to make your simulator reflect the scenario you care about. Here's some simulated data we did. This is a bin with an item in it on a conveyor belt, which is all great, but it appears to be on a Las Vegas casino carpet, which is interesting, but also never going to happen in one of the venues that we actually go into. Right? Mostly we have concrete floors. So this is an example of a mismatch between our simulator and our reality. And so you can spend a lot of simulation time simulating and learning things that you don't need to deal with at all. So we're going to go the next step, and we're going to argue that we can actually collect the annotations directly from the remote intervention process itself. How do we do that? This is the single annotation paradigm. I showed you this image here on the right before. This is a depal setup, bunch of boxes, and we have just one object that's been highlighted by the human. Compare this with this scenario. This is another situation we see. This is a pile of bags. Right? You might look at the boxes and say, oh, that's pretty easy. I challenge you to look at the bags and say, I could do that easily. But we ask people to do this anyway. And if we ask them to annotate every single bag, this takes minutes. But if we ask them to annotate just one bag of their own choosing, pick the easiest one, that's seconds. They can just go in and just do that. And seconds is about the time frame at which we get these requests. So what this means is that we can answer them in real time as they happen without getting a backlog. So it's important to note two things about this single annotation paradigm. One is the response is not the best. We're not asking the human, find the best thing to pick. We're asking them, find us a thing to pick. So it's an adequate response, not a best. Also, the response is not complete. We're not asking for everything. We're asking for minimal time. Do the minimal amount of work as quickly as you can to get us an adequate answer. Well, this is a shift from traditional learning. So how do we actually learn from this data? If you're familiar with deep neural network techniques, they usually require a fully annotated data set where you have all the objects of interest annotated. The way we get around that is fairly simple, and I am obliged to say it's also patent pending. We take the single annotation that we have and a known background and cut and paste them on top of each other. And so we can generate a single item in this bin down here. We can also apply affine transforms and get a bunch of items in this bin. Well, what does this look like when we try to learn? If we did traditional learning, where we have the human take the minutes to annotate everything, and we train a model, we can get a 92% average precision. Average precision, just a measure of how well the model fits the data and predicts on unseen data. Higher is better. 92% is great. We put that in production, it works wonderfully. Our clients are happy. If we use the single annotation data directly and try to learn from it, we get 0. The system does not converge. We can't learn anything. If we do this, cut and paste augmentation with no additional effort, we can get to 75% average precision. Now that isn't really production worthy. That's not something we'd want to put into production. Usually our threshold is 85. But that is certainly a lot better than 0. And what's important to note here is there is 0 additional annotation work that needed to get done. So if you remember this loop, we collected data, we had humans annotate it, quicker training, adaptation. This is how we adapt. We've just done that. We collect the exception data. We have the annotations come along for free during normal operations. And now we have a fully automated, hands-off model adaptation loop. And this just runs in the background. So yeah, we only get to 75% the first time, but then we continue to adapt and continue to get better. And it's all automated with no additional human effort. So to come back to this question, universal or adaptable? The way I think about it now is it really comes down to 2 things. How much control do you have over your input, and how much time do you have? And there's this concept of how long would it take you to get to a sufficiently universal model? Now, the more control you have over your input, if you know you're only handling a certain object or a certain set of objects, it doesn't take that long to build a universal model because you only have a certain number of situations to deal with. The less control you have, when I don't know what's coming down, anything could happen, you need more time. And for production systems, I'm in industry, so I'm trying to sell stuff to people. Anything above this line is product. If I have enough time to make a universal system, given the amount of control I have, I can sell that. Anything below, I can't, because I can't guarantee the system will work. And there has been a lot of effort across many fields, academic and industrial, to push this line down. How do we get to a universal model faster? And that's where simulation came in, simulation data. That's where faster GPUs came in. Can we just train faster? I'm saying there's another way. Same chart. Yeah, above this, that's fine. Build a universal model. But rather than trying to push the time to universal line down, we can say below this, we use an adaptable model. This is a model that's going to change with your distribution. And now that's something I can put into production. There's this concept in parcel handling, one size versus right size. And if any of you have ever received a package from an online retailer, you should understand this pretty quickly. This is a single thing of nail polish inside a giant cardboard box. This is a one size solution. We're going to have a big box that can hold anything we need. And that's sort of a universal model. Many, many, many times, that's going to be too big. You're going to have wasted space, wasted learning capacity. Conversely, a right size box, this is a box that really just fits this Patio Magic green mold and algae killer. That's what you want. It handles only the thing you need to handle and nothing else. That's an adaptable approach. We're going to change the size of our box as needed. So I started with this question of what's your distribution? That's not the question I ask anymore. What I ask now is, how much do you control your distribution? Do you own all the things coming in, or are you being shipped stuff by third parties that you don't control? And how much time do you have? Do you need a system that works tomorrow, or can you wait 3 months while we train something? And so it's the evolution of your distribution that defines your actual system needs. There's some contact info for me if you want to shoot me a line. That's our website. The address is actually in Texas, but I'm based in Colorado, and I will take any questions.
Hello, thanks for the presentation. It was very interesting. And I wanted to have some details on what you used for the simulation. What is your simulation software? And maybe, how did you bootstrap this process?
So for the simulated image I showed, we actually contracted with a third-party company. So there's a company called SBX Robotics that builds simulation systems and will generate simulated data for you. And so we didn't build the simulator ourselves. In-house, we've used, I remember the names. Coppelius Sim, I think was the name of one. We've experimented with Blender and all sorts of graphic FX stuff, but we don't actually currently do any in-house simulation. We've decided that the sim to real gap was too big, and so we're focused on this human in the loop approach instead.
Okay, and so you can generate all your scenarios. Do they do that by hand, or did they use standard tools to do that, or it's really in-house from SBX Robotics?
My understanding is they have a complete simulator setup, like you would see for making movies, and they do very realistic simulations, and then apply a whole bunch of transforms and variants. So we tell them the scenarios we're interested in. We want bins with boxes and conveyor belts. We neglected to tell them that we cared about the floor, right? And that was, we didn't define it well. And so they changed up the floor on us. And then as soon as we saw it, we're like, oh, right, that's not a thing we care about. And so it's this iterative process to get the simulator good. And then we decided, rather than spending all of this time getting a simulator that matches reality, is there a way that we can just learn straight from reality without having to do these heavy human annotation steps? And that's why we developed the single annotation paradigm of, can we just use the data we have that we get during normal operations rather than having to do all this other stuff?
Yes, thank you. Thank you.
Hey, Dan, I mean, thanks for the talk.
Of course.
Are you, who's the algorithm development engineer on your team? Who develops robot motion algorithms, or chooses which ones to work with?
So for robot motion, we rely heavily on the built-in capabilities of the arms themselves. I mentioned we buy our arms from providers like Fanuc or KUKA or ABB. They all have built-in libraries that do motion control and motion planning. For the most part, we focus entirely on telling the arm where it needs to pick up and where it needs to put down, and we let the internal motion plan determine how to get from one to the other. We do have to consider some things like gimbal lock and some orientation. So we do some pre-processing of our points to make sure that there's a valid IK solution. But that's off-the-shelf stuff. That's inverse kinematic solvers. I wouldn't say we developed any of those algorithms ourselves.
I see. Yeah, this is a cool space to be in, warehouse robotics automation, because I mean, you don't have to deal with the humans you don't have to deal with.
It's true. It's collaborative robots, but distal, right? So our humans and our robots are almost never co-located, because the arms themselves are quite powerful and can cause serious injury. So they're still behind cages, but we're doing the human-robot interaction mediated by this yonder system. And it's been really interesting to explore, this isn't the work I talked about here at all, but how do you give this remote human the sense that they're interacting with an entity, like with a robot that is consistent over time, when all they're seeing is an image on a screen? And so it's been, the human aspect of it is sometimes more complicated because they can't actually see the arm, the robot at all. That's like I said, that's a separate area of work, but happy to talk about that or answer questions as well.
one last question. So who is there a person, I mean, I'm guessing it's probably you, who goes over academic literature and says, huh, this looks interesting. Maybe we should figure out how to get this into our systems.
Yeah, actually, so it's me and some others. We've got 3 PhD level ex-academics in the company right now. We have a reading group that meets once a week. It's probably 5 to 8 people show up where we go through academic papers and decide what's useful. The divide between industry and academia is often that academic papers demonstrate it once, and then our question is, can we do this? We do 1.5 million picks a day, so can we do this 1 million times a day reliably? Is often the jump that we have to make. But there's lots of really cool work out there. We read one the other day. All the neural net stuff. We follow NIPS, we follow HRI, we follow RSS and IROS and ICRA. We go through all those papers and try to find things that we think would be applicable.
That sounds pretty good. I mean, if you don't mind sharing your email address again.
Sure, I'll put it in the chat so everyone can see it. I'm on the Talking Robot Slack somewhere. I'm also on the Robotics Worldwide Slack. If people are on that, you can always hit me up and ask me questions. I feel like I should also say I am hiring. So we have a careers page on our website. If you're looking to do this sort of work, come work for me.
I just did, and I did not find I did not find a job that described you meeting for a paper discussion group.
Oh no, that's probably not in the job description. You are correct. That is just an internal thing that we do.
Right, but I'll reach out to you. This is fascinating.
Cool. I see Raphael has a question.
Yeah, hi Dan. Thank you for the presentation. It was really nice. I have a technical question.
Sure.
You mentioned that you're using depth sensors to identify the objects, right? So I was wondering if you use an off-the-shelf post-estimation system or if you built something in-house.
Yeah, clever. You hit on something very interesting there. So we actually only use the color, the RGB, to do our machine learning. So we're detecting in pixel coordinates, and then we use calibrated camera extrinsics to know where they are in the real world.
I see. Okay. So you use like conventional computer vision algorithms to identify the pose from a color image?
We're sort of lucky, and most things we handle are planar. So honestly, we find the object boundaries of the segment in our RGB image, and then we pull the points from the point cloud. We can do conventional point cloud manipulations to find the plane and estimate its normal, and that's all we need.
Okay, that's
once we know the location of the normal, we can put our arm right on it.
Okay, yeah, that's great. The other question was more like, I don't know if I missed that, if you talked about that, but how was did you try the system in the real world, like, and evaluating its performance, and how much better was it compared to an autonomous, fully autonomous system, or did you have any evaluation like that? You mentioned something, million of pickups, something like that before, right? So.
So we are in production. We do 1.5 million picks a day. If you go to our website, you'll see, I think our lifetime total is somewhere 800 million picks in production. This is actual objects picked and shipped through warehouses. We are constantly doing tests in the real world. That's sort of the exciting thing about being in industry is once we are happy with it, we ship it and it is live somewhere. And if it goes wrong, we have to fix it. So we need to be pretty confident it's going to work. So the Yondr-based human in the loop system is live. That's what we do every day. We have a team of people called crew chiefs that are answering these questions from these systems to help them deal with these exceptions and this distribution shift. And that works, I mean, better than a fully autonomous solution because we can handle anything. The way the sales and marketing guys say is, we can be 100% on day one because we always have that human in the back.
And are you aware of any cases where human input was actually bad for the system?
So yeah, humans are humans. They make
Yes.
errors, right?
Okay.
Occasionally we will ask them to find the box and they will not find the box, or they will find something wrong, or they will find the wrong box. And then the nice thing is we are no worse than if the autonomous system did the same thing, right? So often you'll find a box that can't be reached and the IK will fail and the system just will fail to grab it. And then it will ask the human again, hey, that didn't work, give me something else. Very occasionally the human is unable to solve the problem at all. And then they basically push a button that says, I can't do this. And it goes back to that walkout where a human will physically walk out to the system and deal with the issue.
And is it usually that when the remote human mentions that I can't do it, that there is actually something wrong with the configuration that even an autonomous system cannot solve in the warehouse?
Yeah, it tends to fall into one of a few bins. One is there's something physically wrong, like mechanically, we're actually solving the problem. We're telling it where to pick, but the gripper has stopped working. So we can't do that remotely. Or there's something in the scene that's not supposed to be there. So we sometimes ship liquids in boxes and bags, and if they pierce or break, we have a spill, right? And we can't handle those.
Okay.
And actually the whole system needs to be shut down and the cell needs to be cleaned because there's a spill.
Yeah.
Sometimes it is just configuration of like, hey, this box is slightly outside of the configured reachable area of the arm for safety reasons.
Mm-hmm.
So if we change that configuration, perhaps we could have solved this. But for safety reasons, we can't.
Okay, cool. Thank you very much. Thanks.
Of course.
I have a quick question. So I think you talked a lot about warehouse settings and all the scenarios. Do you guys also look into like service robotics where the complexity also increases drastically? And or this is something that you don't go into?
Yeah, so Plus One Robotics, we're focused entirely in warehouses, in induction and decal. That's really all we do. The same techniques could be applicable outside. Right? I personally think human AI symbiotic systems and human-in-the-loop learning can be applied in lots of venues. And if you go back and look at some of my papers, I talk about other venues that this could apply. My work was in RoboCup, playing soccer with robot dogs. But at this company, all we do is warehouse logistics.
Thanks.
I have a couple of questions as well. So one of them was when you mentioned Yonder, do you actually have a time when you finish the training and then is the goal to make it more autonomous and less reliant on people, or do the people are a package, are a part of the package that you offer to the customers?
So the belief is that given the shifting distributions and the long-tailed nature is you will never be able to achieve zero human interventions.
Right.
There's always going to be something novel coming down the line. And so you need the human there. Over time, we expect that to reach some sort of steady state. And the goal is to push that steady state down. I don't think it's going to get to zero. But like if today, I'm making numbers up, but if today it was 10%, if we can push that down to 5%, that's great. But I don't think we're ever going to reach zero.
Right. And the second question was that, do you have one single model that you keep updating every time the human annotates, or do you have like multiple different modules, or do you patch up one thing with another, or like how does that go?
So this is where a lot of the really fun, interesting work happens. So because this update loop, this adaptation loop is fully automated, we run these experiments, right? So the question is, do we take our old model and adapt it? Do we train a new model with this new data? Do we split this model into two and adapt one and not the other? Do we have different models for each cell? Well, now that this whole process is automated, that's just a question of computation time. So we actually run many of these scenarios in parallel and then evaluate the model performance and decide which one to go. I'll say in general, most of the time, this is all building onto one model per sort of scenario, per sort of application. But we do see some that are their distributions are so different that you're better off just making a new model.
All right. Got it. Thank you. Andrew, do you want to go ahead? Maybe I think we have time for one question.
Hey, Stout.
Hey, Dan. Good to see you. Thanks for the talk.
Yeah.
One of the features that I noticed of this system that I think maybe underpins the system is that the supervisory signal coming from the human is quite simple.
Yes.
They can provide it very quickly, very easily. What do you see as the challenges of extending this approach to circumstances where the supervisory signal is more complex? Maybe there's a I don't know, a kinematic aspect to it, or I don't know, something more complicated than segmentation.
Yeah, I think that's spot on. There's this, how long can you wait for a response, and how long does it take the human to make the response? And this number has to be lower than this one. Right? This is why this sort of approach I don't think will work for autonomous driving, right? Because you need the response so quickly that the human can't generate fast enough. And that's the same thing. If you can wait a second, but the task is so complicated that the human takes 10 seconds to do it, I don't think that's a viable area that you can apply this work. So what I'd say is you got to figure out, is there a way that you can either wait longer or make the human faster? But if those are out of balance, you can't do this.
Do you think there's room to apply an approach like this in cases where there isn't a lot of time pressure, but the instruction, the supervisory signal, still takes a long time? Let's say, I don't know, 10 minutes or something like that. Or
Sure.
Does something about the complexity of that signal make this harder?
As long as having the human do it remotely and providing the supervisory signal is faster than the alternative. So, there's this, here's a trivial domain, right? I can either solve this problem and it's going to take me half an hour at home, or I can drive an hour to the place and it'll take me 5 seconds to solve, right? Well, it's still better for me to spend the half an hour doing it from home than driving the hour to the place, because the transport time is just too much. And so if that's a scenario that you're operating in, then this totally makes sense.
Cool, thanks. I guess I'm thinking that there may also be something about the nature. I suspect that you have to break down the problem to the point where the supervisory signal is. I mean, I guess it's the point that you made about it being identical to what the system.
Yeah, it has to be the same. There's some interesting work coming out of various labs on how do you combine sort of different levels of supervision. So instead of this is the answer, maybe the system generates 3 answers and the human picks the best one, which might be faster than having them generate it themselves. So I think there's some things you can do to make the human accomplish the job faster, perhaps not as well, but we don't need perfect. We need adequate, right? So maybe it's pick from one of these 3 or 5 mediocre solutions to the problem rather than give us the best one. That might make the human faster.
Thanks.
Cool.
All right. I think that might be the end of the discussion. So I'm gonna thanks again, Dan, for sharing. And it was a really nice session. I think we all had a great time discussing about your work. And I also want to take a minute, advertising the next session. We have Bruno Adorno joining us in a couple of weeks, and he's from University of Manchester, and he'll be talking about dual quaternions for robotic manipulation. So that's all for the session today. Thanks again for joining, and I hope you all have a really good day.